Well, thank you very much. I really do appreciate the opportunity to come out here and speak. One of the things that you're going to hear me talk a lot about is, I'm at Georgia Tech, so I work in robotics. I've been doing robotics since graduate school, so 30-odd years of doing robotics, and robotics has changed a lot over that time. But one of the things that I really appreciate about coming out and meeting with you guys is I can write papers all day long, and I write a lot of technical papers. I can write proposals, and I write a lot of proposals to the government, NSF, DARPA, and everyone else. But it's when I meet with industry, okay, when I can talk about how we can translate all the really cool things we do in the laboratory, but how can we translate that in the real world? Okay, that's what really gets me excited. And that's one of the things that the IRIM, so the Institute for Robotics and Intelligent Machines, that's what that stands for. That's one of the things that really excites us, is how do we translate all this wonderful technology? Okay. Now, we started IRIM several years ago, and one of the things people always ask me, well, why did you all start it? And the number one reason everyone thinks that we started it was money. Okay. You want to raise money, you're going to bring in more money, or things like this. That was the absolutely wrong reason we started IRIM. The reason we started IRIM was really to focus on these last three areas. One is we had the PhD program. Okay, we're the #2 robotics program in the nation. Signed some school up in Pittsburgh that we don't like to talk about. Okay, but Uber rated all their people, so they're falling. But it's really industry relationships and tech transfer. Now, the reason why we did that is kind of a surprising one. Me, as the individual researcher, it's hard for me to translate technology. Why? Because I'm working on a very specific problem. Okay? But when I started working with my colleagues, okay, well, now I've got somebody who's doing image processing. I got somebody who's doing natural language processing. I got somebody who's doing collaborative robotics. I got somebody who's doing mobility. And so now I can start put all this together into a system. And that's one of the things I've always learned about talking with industry, is everybody wants a system. Okay? Nobody wants to read my paper on visual servoing control, which I think are all outstanding papers, by the way. Okay? But nobody wants to read that. What they want to see is, what can you do? What can you build? How can you integrate this and do something? Okay? And that's what we can do in this institute. We have 70 faculty members, so we're pretty good size. It's not just 3 guys in a basement who decide to start an institute. We're pretty big. We're cross-disciplinary. This is a really big, important point for us. Okay, engineering. We got all the engineering domains. And if you've been at Georgia Tech, we're the #3 engineering school in the nation. And what's different about Georgia Tech is I always like to bring visitors. I had a visitor, a program manager I worked with at USDA. And I brought him around and I said, here is one of our mechanical engineering buildings. And he was like, I thought that was like all of engineering. It's like, no, that's just one mechanical engineering building. We got 3, all that size. And he was just blown away. So when we do this, we talk big departments. But we have all of engineering, mechanical, electrical, aerospace, all of that, to bear. Computer science. We all know how big computer science is. And one of the things that when you hear this presentation, I almost never talk about machine learning and AI. Okay? And everybody always gets upset when I'm done with the presentation. You didn't talk about machine learning. Okay? Machine learning and robotics, we go hand in hand. Okay? I've been doing some form of machine learning for 30-some-odd years. I've done, I did the expert systems. I did fuzzy logic. I did, machine learning, neural nets, everything, you name it, I've done it. Okay? We don't get all of that worked up about machine learning because we've been doing that forever. Okay? So computer science, very much in there. Sciences. Okay? This is something I'm really glad we're working a lot with. And some of the work that I do and some of the work that we do is in agricultural and food. So we work a lot with the University of Georgia. They're the Land Grant Institute. We work with them because they have all the scientists. And they have all the food technologists, microbiologists, plant pathologists, all the things that I don't have at Georgia Tech. All right? But I work with them. We come up with all kinds of interesting ideas because that's where the really cool things happen. When we get people together. So as I said, I was excited talking to you guys. Same thing when I talk to my colleagues. It's getting interesting and different people together is very good. And now even economics. Really glad we got that one in there. Okay? because, as I tell people, I'm an engineer. You know, we're really, really good research engineers. But for some reason, you put a dollar sign in front of the numbers, and we all get confused, you know, and we have trouble with that. So having somebody can come in and help build a business case, help me to understand why solving this problem is really, really important, as opposed to the really cool problem that I wanted to solve, okay, because I thought it was neat, all right? That's what all this is about, okay? And that's why putting together these teams is so very, very important. So, I'm going to talk a little bit about just some of the work that we do at IREM. And I'm going to kind of focus this on this very broad area of collaborative robotics. And for those of you who don't really know what collaborative robotics is, and that's perfectly fine if you don't, I'll just kind of quickly summarize it. Originally, when robotics came out in the 60s and 70s, 80s, and really up until 2010, robotics, if you put a robot in a manufacturing facility, it was put the robot in, put a big fence around it, you know, all the security guards, and dear God, don't let anybody get near that robot. And if you open the door, everything stopped, okay? Because if that robot met the person, the robot beat the person every time. In other words, it just go right through the person, okay? One of the projects I'll show you a little bit later is we decided that wasn't dangerous enough, so we put a scalpel at the end of the robot, okay? So the robot can now stab you. And it doesn't just stab you, it cuts through you. And it does a lot of damage, okay? So, you know, that's a traditional mode of robotics. Nowadays, when robotics, we talk about robots leaving the cage, okay? The robots are going out into the world, okay? And we're doing this in a couple of different ways. One of this is collaborative robotics. And by that I mean the robot can actually sense people. Okay, whether it's perception, it can see you and it can respond to you. We do a lot of human-robot interaction in that area, which is all kind of really bizarre, but it's kind of neat stuff. But it also, there's the control side. If the robot is moving and it makes contact with the person, it stops. It's a really cool concept. Okay, and what that means is you don't need all the safety guarding. Okay, now you can put the human and the robot together doing things. And now you can have the robot doing the things that the robot is really good at doing, and the human doing the things that the human is really good at. Okay? And that brings up lots of very interesting ideas. Because we as humans are really good at a couple of things. We're very good at rational, we interpret things. Our perception is amazing. Our ability to walk into this room, I can identify all the chairs, the water bottles, and stuff, and I don't need a model ahead of time. Okay? Everybody talks about, well, machine learning can do that. Well, machine learning can do that as long as you've had that chair or something really, really close to it in your database. Okay? And the lighting's just right, you know, and somebody's not sitting in the chair's not turned at a weird angle and stuff like this. So there's limitations. But also, like one of the really cool things is a water bottle. Water bottle's transparent. But we as a human, or even a coffee cup, we can look at that and I can estimate how full that cup is. I'm estimating what the coefficient of friction is. Is that bottle wet, slippery? Is it dry? Where's the center of mass going to be? Okay? I'm estimating all that stuff just automatically. But getting a robot to do that's really, really hard. The other thing is grasping. This hand you have is absolutely incredible. So your mind is incredible, we already know that, but your hand, okay? And I'm not going to do that here, so don't anybody panic. But, you know, I can take a ball, or I can take any object, and I can throw it at somebody, okay? And every one of you is going to catch it, okay? But I don't have to tell you ahead of time. All right, I'm launching this at 57.5 degrees with a velocity of 2.5 meters per second, okay? And it's got a weight of 3.2 kilograms. Here's the diameter. Its rotational speed is this. Coefficient of friction is this, and stuff like this. No, you don't do that. You look at the object, you look at your hand, and go move left, move right, expand, contract, and then as you begin to close, you sense. Okay? And your hand is doing a gazillion calculations. You're not consciously thinking of that, but your hand is adapting. Okay? Those two skill sets, your ability to perceive and to be able to do things with your hand, is what makes the human such an incredible machine. Our goal is to try to duplicate some of that. That's a hard problem. So I'm going to talk about a couple of different application areas. The reason why I talk about these is, number one, this is kind of what our researchers are doing in different areas, but also just to kind of expand your mind. What I want you to walk away from this experience, okay, is not that Gary's a great speaker, which I know you're not going to walk away with that theory, that idea. What I want you to walk away is that robotics is changing the world, and that your company needs to understand how it's changing and how it's going to impact you, okay? Because it is coming, okay? So that's what I want to be able to talk about. So the very first thing, and I apologize on this one is a little bit wordy. I understand that. But the main problem about this is today's robots are really brittle. And by brittle, I mean they're really good at moving from point A to point B, okay? That's really what robots do. Robots are essentially blind, no hearing, and really no sense of feeling, okay? But they got really good sensors on their arm, and they can move from one point to another very precisely. So imagine blindfolding yourself and doing this all day. Really, really good at that. The problem is, God help you if that bottle or whatever you're picking up moves, okay? Because now your robot has no idea, okay? And what happens when that happens? The robot shuts down. All the emergency lights come on, and if you've ever been in, I've done some work in the automotive industry, if that auto line goes down because the robot doesn't pick up the part, it shuts down. You've never seen so many guys in suits come running out, okay? Because I think the downtime of automotive used to be $20,000 a minute, okay? A minute? Yeah, that gets a lot of people's attention, okay? That's what I mean by brittle. Okay, it's very easily broken, okay? And the reason we do that is there's really very little sensing. Custom fixtures, okay? Everybody builds jigs and fixtures for everything, okay? Why? Because you want to force the components to be exactly where they need to be. Why? Because your robot doesn't have any sensing, okay? The human doesn't need it, but the robot does, okay? So teach-dependent, programming, that's that little thing that the guys hold and kind of move around. The world's worst programming, environment, it's up there with DOS, from the 80s and 90s. I mean, it's pathetic, but, that's just the way we do things. And then no standardization of programs. So ability to translate a program from one robot to another is pretty much zilch, okay? BMW, when they built the Spartanburg plant, they modeled the facility ahead of time. They did all the simulations of all the robots ahead of time, and they said, we've got this worked out. Here's the one program to handle all the welding. Here's the one program to handle all the handling of the hoods. Here's the one program to do this and that. Turned it on, and it was a nightmare. Robots were running into everything. Why? Well, number one, the floor wasn't level. Okay? That pretty much kills everything right there. Conveyors were not at exactly 90 degrees. Okay? Conveyors were not exactly level, and every robot has a slightly different kinematic model. In other words, you could try to build a robot to be exactly the same, but you can't, okay? So they're always going to be a little bit different. So what they have to do, they had to go back and reprogram everything. So now every robot had its own program, okay? Couldn't switch one program with another, shuts everything down, okay? So that's a big problem. And plus, to program the robot always required the PhD in computer science. Okay, trust me. There was nobody out there who didn't have a PhD in computer science who was programming a robot. Okay, way too complicated. We have these funky things called quaternions. And if anybody here knows what a quaternion is, I'll be really impressed, because it's a nasty thing we invented to be able to understand angles. Okay, but that's what you had to program in. So one of the things I'm going to talk about is the aerospace industry. Boeing is a big customer of Georgia Tech. Boeing has a really big problem in that their airplanes are sold out very nicely, and if you buy a 777 or whatever, the 787, whatever the newer plane is, you can get that plane delivered in anywhere between 5 and 8 years. Okay? There's not many industries that can afford to do that. Okay? And trust me, that's a big problem for them. Okay? So what they want to be able to do is understand, all right, here's their needs. Okay, so if you look at their needs right here, there's nothing on here that's going to be, probably in your industry, nothing in here is going to be radically new. Okay, increased volume, flexible tooling, rapid deployment, safe, certified processes. And then we map that into gaps. Okay, well, what's the gap? You need in-process inspection, foreign object detection. That's a really big problem for them, dust manipulation. And then we map that into R&D. Okay, so what are the R&D projects that need to be done? Okay, and that's how we started working with Boeing. Okay, in other words, we didn't start by trying to say, I'm going to do flexible tooling. Okay, it's just too big of a problem. We tried to break it down into what's the technology components. Okay, if I break it into technology, that's what universities are really good at developing, is technology. I can develop that. Now I can work with the industry and I can integrate that and do something. But I've got to be able to break it down into something which is meaningful to us and serves a purpose for you. So here's some of the things we started working on. I just showed this one just because it was kind of a neat picture of just mobile robotics. Okay, now why did we do this? Okay, the problem was in aerospace and engineering, they had these massive monuments built to holding the wing. And that wing is very precisely held. Okay, it's got to be in the exact right spot. And then they had another monstrous piece of equipment, usually the human or something tried to do with some automation, that did riveting. Okay, riveting is, I mean, it's not rocket science. Okay, but it had to be very, very precisely controlled because you had to, you had to put the rivets in the right spot, had to be at the right angle. Okay, and you know, it's kind of a crucial step. You got to make sure you do it right. All right, so these things were very, very important and controlled. Now we're coming in with mobile robotics. Okay, now I'm sensing where the wing is, not assuming that it's going to be precisely located. I'm imaging where the wing is, matching it with the model, localizing on that, and now doing the riveting. Okay, so now I've gone to something which is these huge monuments, which are multi-million-dollar pieces of equipment, down to some sort of a mobile base with a robotic arm. Okay, now it's down to $50,000, $100,000. Okay, with some sensing. Okay, that's a big improvement. It's a big change, but it's also a big change in their process. Okay, but that's some of the stuff that we're doing with Boeing. Also very involved in some of the standards that are involved. Standards is always the least favorite topic of anybody ever to talk about for lots of reasons, but I try to bring this up for a couple reasons. Number one is what we're trying to do is develop some standard language and what we call ontology, okay? Such that if everybody agrees on certain language, now you can start developing more user code that can be reused on different applications. Okay, so one of the projects that we are doing is this, we're doing a kitting operation. Okay, kitting operation is, I mean, you guys probably know this, so I don't mean to be telling you your own business, but in this case, it's where we take in parts from different boxes or containers, package it into a kit which is being used in the manufacturing facility. Okay, pretty easy for the human to do, obviously also fraught with danger. So we're doing this now, and what we're developing is standard terminology, okay, for what's grasping, what is, how do you define really if you drop something in the middle of the motion? How do you handle the image processing, okay, the data? How do you match it to the CAD data? All these are standardized processes. And then also the code to the robot of moving, okay? How does the robot move from point A to point B? What's really cool about this is I can actually pull out that robot, and that's a FANUC robot right there, and I can put in any robot I want, and the same code works. Okay? Right now, if you go to Ford, General Motors, they are KUKA house, A, B, and B house. It's one robot manufacturer, okay, because you've invested in learning that software language. Now, there's a thing called ROS, which is a robotic operating system, which came out of some startup companies and it's now being heavily used by the academic world, but it's also making its way into the real world. BMW is using it a lot for their autonomous vehicles. Now we have a structure, a language, which is generic, and we can now be able to plug in sensors, So it's great for bringing in the Connect data, 3D data, point clouds, 2D data, camera systems, and can control any type of robot. Okay? So we're moving away from a single program for one task and one robot to this automatic generation of software. Okay? So just by explaining what you want to be able to do. And this is actually one application that we're starting to use this. This is a company called Denso. They are a automotive manufacturer. These are distributors, part of the distributor. They manufacture these up in Maryville, Tennessee. Turns out that there's like 21 different types of distributors that all look remarkably similar, okay, but they have slight variations. So that what they want to be able to do is an imaging system, be able to recognize, pick up those parts, and feed it to a machine. And so here are some of the parts that you see in the container. And then feed it into the machine. Okay, so it's a relatively simple task of just machine tending. Parts go in, parts come out every 6 seconds. Okay, but how do you automate that? How do you add in the error checking? How do you add in this automatic software generation? So if there is a problem, the robot knows there's a problem. It doesn't just shut down and say, hey, something bad has happened, and stop production. Okay, so we're trying to begin to translate these ideas into the real world system. This is another interesting thing that we're doing with Boeing. So this is actually doing some drilling operations. So it's in addition to the project I just described earlier. This one is actually getting sub-millimeter accuracy placement of the robotic arm, and then doing drilling operations where the force is so high that it's actually causing the robot to deform. Okay? And when the robot begins to deform, obviously we lose accuracy. Okay? So what we're trying to do is actually be able to model and predict the deformation of the robot, use real-time controls to be able to adapt that process. So we maintain that sub-millimeter accuracy even as the robot is deflecting under these incredibly high loads. Okay? So this is, again, the types of projects that we're doing is not something that I never would have thought of in my wildest dreams. But when you work with industry, they're saying these are the types of problems that we have. Okay? This is the things that we need help on. Okay? And now we can sit there and look at it, okay, I understand, we can help do these kinds of things. So now we're actually have these robots running in our facility and actually beginning to demo this work. So this is just something I kind of just threw in. We talk about these big robotic arms and stuff. We also do stuff at the nanoscale. Okay, there's a lot of interest in that area. So this is some stuff we're doing at the National Science Foundation, manipulating carbon nanotubes. Okay, I just really kind of threw that in there. We're also doing some work in biological systems, and this is kind of my integration into the food and ag work. Is biology. So I'm an engineer. I know Newton's law. Newton's law works all the time. Of course, as long as you get the units right. So you don't launch your spaceship to Mars and miss by a couple of thousand miles. So as long as you get the units right, F equals ma works all the time. Biology is a crazy, crazy world. Okay? Biology is 1 + 1 = 2 unless it's Tuesday and it's below 50 degrees. Okay? We don't understand biology really very well. Okay? So trying to get robotic systems to be able to work in biology is really, really hard. One of the things that we're doing is in biomanufacturing. Georgia Tech just got a NSF Engineering Research Center in biomanufacturing. So it's a really, really big deal for Georgia Tech. And what we're working on is how do you do stem cell production at scale? Okay, we're pretty good at doing it in the laboratory, but how do you scale that? Okay, the problem is they're getting 65% yield. Okay, it's not very good, and you only have a very finite amount of umbilical cord fluid. So it's not like you can just have 65% and just run it all day long. Okay, very, very limited supply. So how do you have robots that can do the sensing and improve that control? So that's something that we're really working on right here. I'll kind of skip over this a little bit. This is just some of the stuff that we're doing in the human-robot interaction, how machines work with people, okay, and things like this. You know, one of the things we're trying to do is, you know, in a kitchen environment, you know, cooking operations is something which, you know, there's been a number of robotic systems developed to do some very simple cooking operations, because cooking is something which is somewhat a mechanical process, somewhat, okay? But in the food prep side, it's very, very difficult, okay? And that's something that we are very interested in, because that is really, really hard to do. And that it requires more intelligence of the person to be able to operate. But cooking itself, there's a number of people working in that area. I think they're making pretty good progress, but we're starting to work in some of those areas. Just a quick picture of just some of the things we're doing, this biorobotics. One of the things I just want to highlight here is some of the work we're doing in exoskeletons. We're doing some work. Obviously, the government is very involved in some of these things. You know, the Iron Man suit and things like this. Yes, they are working on those things. So exoskeletons, what will the worker of the future be able to do? Okay, and there's not a single manufacturing company I've ever spoken to who was not very interested in what that means to their future operation. Okay, and to be honest with you, we were just starting this area. It's a wide open area. There's a lot of stuff that's coming out of the health community, stroke rehabilitation robotics and things like this has given us a lot of insights on how we do this, but there's still so much more to be done on what we can do. Everything from the controls of the arms and the legs, very different types of control systems and issues, but this is something that we're very actively working, and it's something we are working with companies, because there's a lot of intermediate steps in there. I've seen some colleagues who did some very simple robotics where they just mounted a robotic arm to the shoulder because they were doing an operation above their head. So they just mounted two lightweight robotic arms that would hold the piece up, okay, so that they could then go get their tools and then, you know, drill holes and do whatever they needed to do, okay? I thought that was pretty cool, okay? Because that's right there is, you know, those of us, you know, have you ever done that kind of work above your head? It's really, really hard, okay? Having something that can help you was very nice, and something that's smart and intelligent, okay? That's the key. You can't just put something up there. It's got to be something intelligent. So that's something that we're working on. Kind of getting more to the food the kinds of things. One of the things that's really kind of intrigued us about food is that, you know, robotics has been very successful in the automotive and electronics industry. Why? Because you're dealing with things which are very rigid, very well defined. They're dry. You've got a CAD drawing. Okay, so I can take an image, I can match it to the CAD drawing, and know exactly what piece I'm picking up. Okay, I had a vice president of GM who one time told me, I just want a camera system that could take a picture of the screw and tell me what part that came from. Okay, so they can go find the car and see if it's missing a screw, or at least they know where to put it so they could reuse it. Okay, so there's you know, but that's really an easy thing to do. But you're dealing with food. So one of the things we do is we do a lot of work with the poultry industry. Poultry is huge in the state of Georgia. If we were our own country, we'd be the 7th largest producer of poultry in the world. Okay, poultry, it's wet, it's deformable. There's no CAD model. Okay, there's nothing standard about anything in poultry. Okay, so trying to image it and grasp it is really, so from a research point of view, it's a great industry to work from. At dinner parties, I'm a horrible guest, okay, because I want to talk about that kind of things. But from research, it's really good. So we're doing some stuff. You'll notice this is the Baxter robot, the very first collaborative robotic system. 2 robotic arms, cost $25,000, okay? Big improvement over the traditional $100,000 robotic arms. Okay, trying to pick up what we call the front half of the bird, which is from the rib cage to the neck. It's been eviscerated, so there's nothing on the inside. What that means, if you squeeze it too hard, it squirts out. Okay, so it's a very hard task. So, so this is the video of a cutting project. So this is actual workers in a poultry processing. They cut one bird, it's coming every 2 seconds, where they have to do one every 4. So it's just like carving a turkey. Okay, if you ever carved a turkey for the holidays, you look at that bird and you look and you say, all right, well, here's where I'm going to start cutting. You put the blade in and then use that sense of feel to be able to cut. Okay, those of you who only carve a turkey once a year, you're probably pretty bad at it. Okay, I'm pretty bad at this. These workers are doing one every 2 seconds. They're really good at it. Okay, problem is it's an ergonomic nightmare, and the yield is really, really bad. Now, they do really great the first 5 minutes of the day. Okay, but after about 2 hours of doing this, you know, their performance plummets. We actually did a big data collection on this, and it's really funny. I always kind of compare it to Tiger Woods. Okay, when the guy starts, it's Tiger Woods pre-divorce. I mean, that swing looks great. Okay, I mean, it's precise, motion's on target. And after about an hour and a half, it's Tiger Woods post-divorce. I mean, it's just all over the place. You have no idea where that blade's going to go. Okay, what that means is the yield drops. 1% yield loss is $2 million on an annual basis per plant. There's 22 processing plants in the state of Georgia. Okay, average yield loss is 4%. Okay, that's with the person. So the person, the best the person can do is 4%. But when they're losing focus, it's 6 to 8%. So we can consistently hit 4%. So we can match the person's performance right now, and we can match their speed as well. So, but it's a combination of image processing. So what we do is we actually take a picture of the bird, and we use modeling to be able to predict the interior structure of the birds. So we predict where the tendons and the ligaments are down to plus or minus 3 millimeters, and then rely on high-speed force feedback. All the interesting stuff happens in the first 100 milliseconds. Okay, so it's a pretty high-speed task. This is some work that we're doing in imaging. I like to show this one just because what we solved was not the problem we started out to solve. Okay, the problem we wanted to solve was bone chips. Okay, when they debone the bird, if they cut incorrectly, you get a bone chip. So they have X-ray systems to try to find all the bone chips, because you bite into Chick-fil-A, you don't want the bone chip. Okay, so X-ray systems are really, really expensive and really hard to find the bones. So either you crank up the intensity, but then you get cartilage and everything else that's in there, or you turn it down and then you miss some of the really small bones. Okay, so there's no happy medium in there. So our original idea was we would backlight the bird. It kind of looks like an X-ray image. Okay, so just like the old thing about instead of trying to find the needle in a haystack, see if the needle's missing. Look on there and see if the bone is there. If the bone is there, then you know it's not in the chicken. Okay, so we thought that was a really cool idea. Okay, so we showed it to a bunch of people. We went out in the field, took data, and they all went, "Yeah, thanks for coming." And then one of the guys at the poultry industry said, "Hey, can you predict yield on that?" And we said, "Well, what do you mean?" He goes, "Well, you've kind of got this image in kind of light and dark areas. Can you tell how much meat is left on the bird?" We said, "Well, yeah, why do you want that?" He goes, "Right now, in a modern poultry processing plant, the only way they measure yield is they estimate the number of birds that came in every day. They estimate, they have some measure of the amount of weight that's being processed, and then they divide the numbers at the end by what came out. And that was their yield. The next day, they got that number. Okay? And they were sitting there going, "Hey, can you give us an online yield measurement? Every bird?" Well, yeah. So we started working on that. And actually, that's what this system is right here. So it's actually being commercialized, and it's being sold by a company here in the state of Georgia, and it's just running through, and it's doing an online yield measurement. Okay? Again, it's not the project I woke up, one Monday morning and said, "Hey, we're going to do a yield measurement." Everybody went, "Yay!" That's not what happened. Okay? We went out with one idea. Industry came back and said, "No, that's the wrong idea. Can you do this?" And we pivoted, and sure enough, we could do it, and now it's being commercialized. So I just like to talk about that. here's just some more pictures of the system and stuff. I know I'm running out of time. So this is some stuff we're also doing in disease and pest detection. Again, you know, you're all going to kind of look at me, you know, and go, well, what the heck does this have to do with anything? Okay. One of the reasons I like to talk about this is we're doing a couple things. One is we're flying UAVs over the crops. When we fly over the crops, I'm actually building four-dimensional maps of every plant in the field. And then I'm looking at the growth rate of every plant. Okay? The growth rate is always an early indicator of something's going wrong with the plant. It doesn't tell me what it is, but it tells me something's going wrong. Okay? And the problem is nobody can see that right now. It's like I tell people, I've got 2 teenage boys. Okay? I cannot see them grow. I take them to the grandparents' house and they're like, oh my God, you've grown so much. And I'm like, well, I guess so. I bought you 3 new pairs of pants, 5 pairs of shoes. You know, you're eating me out of house and home, you know, and stuff. But I can't see that. It's the same thing with the farmer. It's the same thing with every process, every manufacturing plant I've ever been to. You can't see these things. Okay? But with the right sensing and the right data, you can begin to see these things. And the other thing I like to do is I like to show this video right here. So this is a leaf picking robot. Okay, turns out in a thing called abiotic stress, which is soil nutrient deficiencies, the only way they can determine if there's that problem is they need a leaf sample and a soil sample. They can bring that back, run it to a lab, a piece of equipment, destructive test, and they can tell that that plant is missing something. The problem is, how do you pick that leaf? Now, there's not a 5-year-old in the world that you can't take out to any field in the world and tell them to pick 5 leaves, and they're not going to come back with 5 leaves. Well, my kids will come back with 10, but but they're going to come back with some number. Okay, trying to get a robot to do that because you don't know where the leaves are ahead of time. Okay, there's this thing called wind that moves the leaves around. The sun, it's not perfect lighting conditions. Okay, so the sun is not directly overhead. It can be in front of you, it can be behind you. The clouds are coming. All these kinds of real-world lighting conditions are really, really hard. But we're doing it. Okay, that robot is actually identifying a very specific leaf. It's not just randomly reaching in and grabbing a leaf. It's identifying very specific leaves, reaching in and picking out that leaf. And actually, some subsequent work, we're actually doing diseased leaves and healthy leaves. Okay, so we're using machine learning. I did use that word. To be able to do that separation of what's healthy and what's not healthy. Okay, and then be able to do that grasping. So this is a system I'd like to talk about just real quickly, just because it's kind of a neat idea. When we talk about robotics, we always talk about mobile robots, those wheels, or I talk about fixed robot, this traditional robotic arm just sitting there. This is actually brachiating, which just means swinging robot. Okay, so what this robot does is it actually, so this is actually over a soybean. We had an agriculture application. But it swings on the cable and moves around. Okay? Now, you're all probably sitting there because I've seen comments on our YouTube video of this is the dumbest project ever invented. So it wasn't quite the exact words, but it's something pretty similar. Why do we do that? Number one is swinging is a very, very efficient mode. From an energy point of view, it's much more efficient. Number two, if I can do everything from above the plant, that means I don't need to leave rows or space in there for my tractor. Turns out if I do that, I can get 10 to 15% yield increase immediately. Okay? We need 75% more food by 2050 to feed the world. I can get 15% like that. Okay? Big, big increase in yield. If I can monitor and do everything from above. I can put a camera on that. I can actually go down into the plant. I can do things. I can prune. I can maybe even harvest. I can do a lot of things. Plus, I get persistent surveillance. Okay? And I don't do that with the UAV, which can fly for 12 minutes and then has to sit down and recharge. Okay? I can sit there and do that all day long. Okay? So that type of ability is really very interesting. So one of the things we're looking at is just in the manufacturing environment, flying a UAV is probably not the most efficient way of doing things. But can I put swinging robots? Can I put robots up on cables? You know, if any of you have ever seen a sporting game, you've seen those TV cameras. It's on 4 cables. Turns out that it can support 17 acres worth of space. You know, can you move, you know, a camera around and things like this? And it's a controls problem, okay, but that's a robot problem. I can solve the robot problem, okay? But now it's just an interesting way of being able to do things. Now a lot of people are coming to us and saying, hey, can I watch people? I'm very interested in safety, okay, what people are doing. I'm very interested in monitoring where my parts are. You know, what's my throughput on these things? When are the parts being used? When are they not being used? Where are things being stored? Okay, how can I be more efficient in my floor space? That now I suddenly have data to be able to do that. And then finally, this is I think one of the last ones, is we're actually doing stuff in poultry in grow-out houses. So we've spoken a lot about human and robot interactions, a lot of stuff on robot to robot, but nothing about robots and animals, okay, working together. So this is actually going into a poultry grow-out house where the birds are grown, from chicks up to broiler meat that we eat. So it happens in about 6 weeks. So putting those robots in there, we put those robots in there, now I can start collecting data. And that data includes 3D models. I can start doing early disease detection. Turns out that chickens, they make very unique sounds. Okay? Turns out there's 21 different clucking sounds. Yes, I talked to the guys at UGA. So I know this. So, but I can't tell that difference. Okay? But the robot in the computer can. Okay, so now I can start telling when the chickens are happy, when they're sick, when the temperature goes up, when the ammonia level goes up. Okay, they'll make different sounds immediately. Okay, we can begin to detect these kinds of things. Okay, so also the drug companies are very interested in that. How do they be able to measure the effectiveness of their drugs and things like this? So, you know, once the robots get out there and we can show that everything works in these environments, then it's all about the data. Okay, what are the sensors you're going to put on there? What's the data you're going to collect? Okay, so, you know, many times I always tell people, you know, I'm a robotics guy, but robots is sometimes the least interesting part of my projects. Okay, it's the sensors, it's the data. Okay, I can collect data. I'm not talking about data, information. How do I turn all that data? In this case, I can collect all kinds of environmental data, audio data, and image data. How do I convert that into that bird is sick, or these birds are struggling because of ammonia levels? How can I, you know, translate that into water? There's something wrong with the water pump. Okay, so they're just not getting water. Okay, and that's really, really important. So, and then finally, I just want to talk just a little bit. We also do a lot of work in environmental and food safety, and I know I'm going over, I'm sorry. So a lot of stuff on sensors for food safety and these kinds of things, rapid detection, okay? You know, food is one of those things of you can sample, but you have to go send it off to the lab to be able to process. A lot of the poultry guys do sample and hold. They'll sample, hold it for 24 or 48 hours before they release it. Supply chain, all kinds of issues with food is the one thing that can actually change in the supply chain to the point where it can kill you. Okay, TVs don't do that. Okay, food does. So how do you sense these kinds of things? So a lot of work we do is in rapid detection of pathogens and chemicals coming off of the process and things like this. So a lot of our work goes into that area as well. So we have a full team, a lot of stuff in nanoparticles, looking at extraction of phosphorus and things like this from the waste stream to be able to make the process better. Phosphorus is obviously a very big problem that is affecting a lot of different industries. And that's it. So I apologize for running over a little bit, but I hope that you kind of got a flavor of that robotics is changing. You know, it's not that same robot that, you know, you see. It's also not the Terminator, okay? And that's the other thing I always try to tell people is, you know, we're not at the Terminator yet. I mean, we don't have robots that can do everything. You know, you walk in and see everything and talk. It's still very limited in what we can do, but we can do a lot more than you think.